Hello everyone, how are you doing? All are doing good? All are doing great? That's good, my dear, that's good. I'm Mahesh, your physics teacher, and you're watching SMR Online Physics. I've been dealing with the topic of light, reflection and refraction of light. And in the last class, if you have watched it, great. If you haven't watched it, do watch it, okay? We are talking about refraction, the Snell's law, and the refractive index concept, right? So if you're new to this channel, please like, share and subscribe my channel for very interesting video classes, which I hope will be definitely helpful to all of you, right? So without delaying any further, let's get started with today's class. Today's topic will be refraction of light by a rectangular glass slab, right? Refraction of light by a thick piece of glass, I mean to say, which is well known by the name rectangular glass slab. Okay, how does a ray of light actually propagate through a rectangular glass slab? I will be discussing about it in details. So let's get started. So when I talk about a rectangular glass slab, my dear, it looks something like this. Let me try to draw a 3D visual of a rectangular glass slab. Yeah, as the name itself suggests, the geometrical shape is a rectangle. Alright, is that good to you? Okay, let me get it straight. This is your rectangle. To give you a 3D feeling, it will have length, breadth and height, or what we call as depth 2. So this is made up of dense flint glass, very thick piece of glass, which is also a transparent media through which light can easily propagate. This is how it will look like in your 3D visuals. Okay, definitely it's available in your school labs. Do watch it through. There's a very good experiment how to trace the path of a ray of light through a rectangular glass slab. So without the experiment, also with the idea of refractive index, or we call as optical densities of the medium, we can easily trace the path of a ray of light. All you have to do is try to visualize the thing very correctly. This is the outer medium, so let me name it. This is your medium 1, which is your air medium. This is your medium 2. So let us visualize it right, that it is made up of a good quality glass. And again, the third medium in consideration is the same as the first, air, glass, air. So when I say air, glass, air, my dear students immediately pick it up which one is optically rarer and which one is optically denser. So let us visualize the condition. Suppose a ray of light incident obliquely on one of the parallel faces of the glass slab. Alright? So if it is incident upon this face of the glass slab, then definitely try to show it with the help of a normal. The normal making an angle of 90 degrees with the surface. So this ray of light, instead of going straight, we all know that, those who have been following class sincerely, that this ray of light in reality does not go actually straight out. There is a visualized imaginary straight path. So actually the ray of light is going from air to glass medium. So it is going from optically rarer to optically denser medium, or we can say it is going from lesser refractive index to higher refractive index medium. So in such a case, the speed of light in the denser medium is going to slow down. The wavelength of the light is going to decrease. So we'll show it with the help of a bent direction, as if it has bent towards the normal. That's it. So this would be the refracted ray of light. Alright? So now instead of again this ray of light going straight throughout it, this ray is actually traveling right inside the glass slab. Again, for my reference, I draw this perpendicular line. My dear, I am drawing a very 3D diagram. If you can, it will be great to draw that. Otherwise, you can just go with your textbooks as you wish like. Okay. So instead of going straight through that, now this ray of light is going to go from optically denser to optically rarer medium. So slow speed back to high speed. Mind it, the first and the third medium is exactly the same. It means that the speed of light, what it was in the first medium, should be exactly the same when it comes out of the second parallel phase of the glass slab. So you're going to get a ray of light refracting away from the normal. That's it. This is how it refracts away from the normal, and you can clearly see the various angles as I will name it quickly. So let us call this ray as P, the point of incidence Q, this point of incidence R, this point of emergence called as S. Alright? So let us name it PQ. PQ is called as the incident ray of light. So this is my first normal N prime. So the angle between the normal and the incident ray of light is called as your angle of incidence. So in the diagram, there is angle PQN should be called as angle of incidence. Alright, good. Now this ray of light passing from Q to R. The ray of light QR, my dear, should be called as a refracted ray of light. The angle between the normal and the refracted ray, this angle should be called as angle of refraction. So in terms of geometrical language, angle M prime QR should be called as angle of refraction. That's good. Now again you see that this ray of light, the QR, behaves like an incident ray for the second parallel phase of the glass slab and finally emerges out. So the ray of light RS is called as the emergent ray of light. Okay, finally emerges out of the glass slab. So the angle between the normal and the emergent ray, this is basically denoted by the small e, so which we call as let me just put a name here. The normal is M dash. So we can call angle M dash RS is our angle of emergence. Alright? That's it. So those are the rays of the light, and these are the three angles which we have to note down. Okay? So it's very easy to see that the final emergent ray of light and the original direction of the ray of light PQ, which I have drawn as dotted line, both exactly come out to be parallel to each other, even though they are laterally displaced. So I mean to say there is always a small distance between these two directions. So this direction, which I denote by small l, the small l in the diagram refers to lateral displacement. So we will talk about each and every part of this diagram in detail. First of all, you please note down this 3D visualized diagram, how a ray of light. Alright, if you are done with it, then I can move forward. Now in this diagram, my dear, let me rub off these names. I'm sure that you have noted it down. So let us, after knowing the names of the angles and the rays, now let us proceed forward. What does this rectangular glass slab refraction actually teaches us? In this device, you will see that the direction of the incident ray and the emergent ray comes out parallel to each other. So since they are parallel to each other, so geometrically you will find that the angle of incidence by measure is exactly equal to the angle of emergence in this case. That's it. That will be equal geometrically, or you could have said the opposite thing, they will be coming up parallel. Why it is so? Let me first of all talk theoretically, then I will show you a beautiful proof also. Why it is so like? The simple reason is the opposite faces of the glass slab are parallel to each other, point 1. Point 2, when the ray of light passes from air to glass, rarer to denser medium, it bends towards the normal. So it is bending and creating a small angle of deviation, delta, at the first phase. Good. Now the same ray of light traveling from glass back to the same kind of air medium at the second interface, you will find that it will be bending now away from the normal because it's going from denser to rarer medium. So this was the intended direction where it goes that way. So this tiny angle will be your angle of deviation. So my dear, it's very easy to see now. The angle of deviation of the ray of light at the first phase and happening at the second phase is exactly equal but opposite, since the opposite phases are parallel to each other. So since the angle of deviation is exactly opposite to each other, even though they are deviating by exactly the same amount, but since they are opposite to each other, yes, you'll always find the emergent ray emerges parallel to the original direction of incident ray. So because of that, mathematically, both the angles are also equal. So let us prove it mathematically, which convinces many of the students. Let us say the first medium has a refractive index N1. The second medium, of which the glass slab is made up of, is a refractive index of N2. And the third medium, even if I call it as N3, we all know that here you can see the simple proof. N1 is definitely equal to N3. It's like given in the condition, right? Okay. Now let us do it for the first phase. For the first surface or the first interface, as you will say, apply Snell's law. So by Snell's law, if you observe and write an equation for the refractive index, then I should find what? N2 by N1 should be equal to sine I by sine of R. Simple. You know that? Good. So let us call it as equation number 1. For the second surface, or you say the second interface, okay, come on. So we can say now it's going from denser to rarer. So I will say N3 by N2 should be equal to. So if this is R, definitely my dear, already have cracked it, this has to be R, because you can see that the normals are parallel to each other and this refracted ray behaves like a transverse. So I think this alternate angles has to be equal. So we'll write sine R by sine E, equation number 2. Is that all right? So from this situation, I can see what we can write here. Since N1 and N3 are exactly equal to each other, so from equation 2, even if I replace this N3 by N1, I find N1 by N2 is equals to sine R by sine of E. We can do that, okay? You got my point. This I have replaced with N1. So here I have N2 by N1, here I have N1 by N2. So if I have to make it N2 by N1 just to match up the sides, then it becomes sine E by sine of R. So let us call it equation number 3. Okay, my dear, is that visible to you? Great, great, great. So from 1 and 3, let me just rub off this upper portion. Okay, from 1 and 3, we can easily see that N2 by N1, left hand side is the same. So we can say sine I by sine R should be equal to sine E by sine of R. So the denominator gets cancelled. Sine I is equals to sine of E. So hence you can say the measure of the angle I should be equal to measure of the angle E. Very simple proof. I hope we got it right. Okay, now I'm going to rub off this thing, and yeah, that's good, yeah. Why to disturb that diagram? That was all good, because I can still use the diagram to discuss the other part of it. What is the other part? Yeah, let me just redraw this part which got rubbed off. This is my incident ray of light. This is your angle of incidence. This is your normal. This is your air medium. All good. Correct. Now let us talk about this lateral displacement. This perpendicular distance, listen carefully. The perpendicular distance between the emergent ray and the direction of the incident ray produced forward. This distance is called lateral displacement. Lateral displacement, the perpendicular distance, as I said, which I am denoting by L, depends on three factors. Depends upon the three factors. Number one, yes, it depends upon how large is your angle of incidence. That is angle of I, and it is directly proportional to the angle of incidence. It means that larger is the angle of incidence, larger will be the lateral displacement. Number two, it depends upon the refractive index of the material of glass slab. Right? It depends upon the refractive index of the material of glass slab. Greater the refractive index, larger will be the lateral displacement. But my dear, we are talking about light, and light can come in different colors. You know the rainbow colors? Violet, indigo, blue, green, yellow, orange, red. So they all have different wavelengths. In my previous video classes, I have also discussed that refractive index is getting affected by the wavelength. So what was the relation? N, the refractive index N, is always inversely proportional to lambda. Clear? Shorter the wavelength, greater the refractive index. So it means that for violet color, as you already know, it has the smallest of all wavelengths than in comparison to red color. So it means that the refractive index for violet color is greatest than for the red color. The two extreme colors, end colors of the spectrum. So if N for V is the largest, then you'll also find the lateral displacement is the largest for violet colored light and least for the red colored light. Extremely important point which I am discussing with you. Alright. So at the same time, the third factor on which this lateral displacement depends upon is called as the thickness of the glass slab. How thick is the glass slab, which I am denoting by T. So here I am writing the third factor is the thickness of the glass slab. And all these three factors, the lateral displacement is directly proportional. Means, hope you are done doing this. Now I am going to prove you and give you a nice little formula for calculating the lateral displacement. Alright, so let me rub off this and use the diagram to calculate the formula for lateral displacement. Okay, as I told you, the factors. So let us do it quick and smooth. Alright, so now I will be making small changes to this diagram so that we can do it geometrically perfectly. So everything was perfect. Let me use this pink color. From here where it strikes, I'd like to draw a perpendicular line onto that produced ray of light. Okay, that makes an angle of 90 degrees. And let me produce this normal till bottom down and remove this and N prime over there. We can write here, this is another 90 degrees. This is N prime. Hope my diagram is very crystal clear to you. I've drawn a beautiful diagram, I hope so, in 3D, okay? Now you can visualize the conditions. So did we give some names? So our target will be to find out what is this RA. This is what I called as lateral displacement L. So our target is to find an expression, find RA. That is called as lateral displacement. Again, my dear, we have been using a lot of geometry. We are doing, in fact, geometrical optics. So, first of all, what I would like to do is that here you can clearly see from the geometry of the angles, angle I can be easily written as a sum of R plus delta, from where I get delta is equals to I minus R. No surprise, that's all good. So now in the triangle, let me quickly write down this triangle. In triangle, RAQ, this is your 90, this is your delta. So what I want here is that I want this, and I don't know both of them, so this is perpendicular by hypotenuse, so let us try to do that. Write sine of delta here. If I write sine of delta, I will get perpendicular RA by the hypotenuse, that is QR. All good. But I don't know what is this QR, so let me leave it over here and go to this beside triangle. You see this? This is another right angle triangle. So in the another right angle triangle, Q and prime R. Q and prime R, I can easily see this is your angle R. So I can write, I want this side. And I know this. This is my thickness. This is the thickness of the glass slab. So this is your angle. So it will be based by hypotenuse. So better go to take cosine of R. So you will get Q and prime by the hypotenuse, that is QR. So this is your equation number 2. So in both the cases you will see that this is our common factor QR. So from 1 and 2 I can easily write, from 1 and 2 I can write QR is equals to RA by sine of delta, and this goes up, you will write Q and prime by cosine of R. So what I wanted here is RA, okay? Are you following? Come on. RA is this the lateral displacement. So RA should be written as sine of delta multiplied with Q and prime divided by cosine of R. I think that's visible to you here. So RA, my dear, I have taken it as small l, the lateral displacement, do not get confused up. Sine of delta, Q and prime is my thickness, so let me write it there, Q and prime T, sine delta can be replaced as I minus R divided by cosine of R. This is the little beautiful expression for calculating the lateral displacement. L equals T sine I minus R by cosine of R. Hope I am very clear to you. Okay. So please note it down. If you have any issues, any comments, do not forget to write in the comment sections below. We'll talk about a small effect of refraction in a diagrammatic way and find a relation between the real depth and the apparent depth. Do you remember when you saw the swimming pool water for the first time? You always find that the swimming pool appears to be shallow. Shallow means less deeper, because the bottom of the swimming pool looks slightly upraised, giving you an illusion that it is not that deep. So that is what you are feeling out from the air medium is called as an apparent depth of the swimming pool. The real depth is actually quite larger, and that can be dangerous. So do not jump into swimming pools without the idea of physics. Great. So finding a relationship between real depth and apparent depth. Okay. This is one of the common illusions we get to see of light refracting between two transparent media. So let's find out a beautiful relationship. It will be helpful in many of the cases. For that I need to draw a beautiful diagram. So this straight line will indicate for the interface separating the two mediums. So let us say this is the bottom of your tank, whatever you feel like. So at the bottom of it you have this maybe a coin right on the floor, a coin which is right on the floor. So definitely this is what I called by the term. I will write a shortcut, okay? RD, the real depth of the coin. This is your coin over here. Okay, great. And this is all water. This is all clean water. Definitely a person outside this chamber can see this coin crystal clear. So how does the ray of light actually travel? Let us choose a tip of it, maybe from here. A ray of light beginning its journey obliquely from the coin. This is the intended normal. So definitely it's going from optically denser to optically rarer medium. So it's going to bend away from the normal. The speed of light is going to increase, and these rays of light actually fall in the observer's eye. That's it. So if someone actually observes this coin vertically straight up, and we know that a ray of light going vertically straight out does not really bend, but in fact the speed of light changes. This is how it looks like. So if I produce this ray of light backward, geometrically believing light always travels in straight lines, you find that this is where it meets light. So it means that the coin is looking upraised to all of us. So it is where the coin is right now. So this position of the coin where it looks right now is called as your apparent position. So this depth from the top surface up, this is what I will call as AD. AD indicating for apparent depth. Crystal clear? Okay, let us put some alphabetical names quickly. So let us call these as P, this is Q, this is like your R, this is like your S, this is making an angle of 90 degrees. So if this ray of light is making an angle of incidence I over there, then this angle also has to be equal to I. That's it. Already in the previous case we utilized it. If this is the angle of refraction, and observe this angle also has to be the same angle of R. All good? Come on. Let's quickly finish it up. So you find here that there are two triangles coming up. So let me write down the names of the triangles clearly. In the triangle PSQ, in the triangle PSQ. Okay, come on. You can tell me what to be taken over here. If I take, for example, sine of I, what happens if I take sine of I? Sine of I is perpendicular by hypotenuse. This is this by this. You don't know all this. So if I take perpendicular sine I, this is then SQ perpendicular by hypotenuse, that is by PQ, equation 1. In the another triangle which is hidden over there is RSQ, the smaller one, RSQ. In this triangle, if I take up sine of R, then I find SQ perpendicular by hypotenuse is RQ. So you see this equation carefully. You will find that we have a common side over there. There is SQ. SQ is common over there. So from 1 and 2, looking into the common side, we can write PQ. What is PQ there? This one. PQ sine I should be equal to RQ sine R. So let us keep it in a box. PQ sine I should be equal to RQ sine R. Now since the points actually in reality, since S and Q are very close to each other, So you are almost looking into the coin, into the tank of water, vertically straight up. So in such case, these 2 points are equal. So we can say this RQ is literally equivalent to the distance RS, and this distance called PQ is literally equivalent to the distance PS. Clear? Yeah, good. RQ should be equal to RS, PQ should be equal to PS. So going back to this boxed equation, so now I can write in place of PQ, PS sine of I should be equal to RS sine of R. Is it good? Okay. So just rearranging it, sine I by sine R should be equal to RS by PS. What is RS? Yeah, AD, that is my apparent depth. What is this PS? That is my real depth. What is sine I by sine R, my dear? Sine I by sine R. If this is your rarer medium air, and if this is your water, denser medium. So if you are taking sine I by sine R, you are literally calculating what? The refractive index of water with respect to air is actually, RS. RS referring to the apparent depth by the real depth. That's it. If you are doing this, refractive index of water with respect to air, sine I by sine R. Alright, am I doing correct? If I am doing sine I by sine R, I am actually calculating refractive index of medium 2 with respect to medium 1. Wait a second, I got it wrong. It should have been refractive index of air with respect to water. Now I am clear. Refractive index of air with respect to water should be sine I by sine R. So that should be apparent depth by real depth. Okay. Now refractive index of air with respect to water, or better to say, you want the reciprocal of it. Or you could have said from here, come on, 1 by refractive index of water with respect to air is equals to apparent depth by real depth. Simple. So from here you can easily see that refractive index of the optically denser medium, should be equal to real depth by apparent depth. So we are interested in finding out the apparent depth here. So I could have also written apparent depth should be equal to real depth by the refractive index of the denser medium. Okay, I hope I'm not too quick to not jumping upon. I'm very clear, please. So that's the way to calculate the apparent depth and the relationship between the real and the apparent depth, which also gives you another new tool to find out the refractive index of the denser medium in concern. Alright. So now what has exactly happened? Coming back to the diagram, the actual object is here, the coin or whatever it is, right at the floor. It is the actual real depth. But to you, the outsider who is viewing from the air medium, he finds that the object has slightly shifted from here to here. This change in its position of the image, what I get to see as an illusion, this change is what we call as the shift in the position. So let us give it a name like, we have the name Pi. So if you really want to calculate the shift in the position, the shift has to be equal to what? The real depth minus the apparent depth. It means it should be equal to PS minus Rs. So the shift in the diagram is nothing but your PR. Am I clear? This PR is your shift. So that is equal to this minus this. Real depth minus apparent depth. So PS is nothing but your real depth minus RS is nothing but your apparent depth. My dear, do not get confused with RD and AD, okay? I'm making it audible very clearly. Okay, so let us find out the shift here. So the shift PR is equals to RD is over here minus apparent depth. The formula is shining right on the top. So that is equal to RD by NW. The refractive index of water, you can say, or the refractive index of the denser medium in concern. So we can say the shift is definitely equal to the real depth in common 1 minus 1 by ND, where ND will represent for the refractive index of the denser medium in the concern. This is the shift you will find in the position of the image. Real depth into 1 minus 1 by ND. Is that clear, my dear? Hope I am clear. Okay, I am helpful to you. Please. It for this class. See you again in my next class. Hope you enjoyed my class. If you like it, do share it among your friend circle, and don't forget to subscribe my channel if you are a new viewer to my channel. Okay, don't forget to press the bell icon notification also to get the latest videos as soon as they are published. So see you again. Stay fit, stay healthy, and remember the motto of this class is physics should stay fun to learn. Okay, see you again. Stay safe. Bye.